Hello, in this video we're going to talk about convergence tests for series. We started talking about what series are a while back, and last time we talked about series and how the Cauchy criterion tells us whether a sequence or a series converges or not. So what we're going to do today is we're going to go over some tests for convergence of series, and we will do some examples. And in the next video, we're also going to continue with more convergence tests for series. The first test for convergence, which is in fact a test for divergence, it would be more. This would be mostly used when we want to show a series is divergent. This test tells us that if a series converges, then each of the terms must approach 0. And if you turn that and take it into the contrapositive, look at the contrapositive of this statement. Contrapositive becomes if an does not converge to 0, then the series diverges or does not converge. Okay, so let's look at the series and see what happens if the series converges. So suppose the series converges to some number a. So this means by definition Sn converges to a, where Sn is just a k equals 0 to n. So this is what it means for a series to converge. Now if you look at the nth term of the series, an is Sn, the nth partial sum, minus Sn minus 1. But since Sn minus 1 is basically the same sequence, this is for all n greater than or equal to 1, Sn minus 1 is the same sequence as Sn. So Sn minus 1 also approaches a. So this means limit of an as n approaches infinity is going to be a minus a, which is 0, and that completes the proof. So if a series converges, then the nth term approaches 0. Contrapositive of that statement would be if an does not converge to 0, then the series diverges. Okay, and that's the part that in fact is called the test for divergence. This is the more useful part of this theorem. Okay, let's apply that in this example. Given a real number r, prove that the sum of Rn when n equals 0 to infinity converges if and only if absolute value of r is less than 1. So we will have to show this series converges if absolute value of r is less than 1, and diverges if absolute value of r is more than 1. So the part about showing that the series converges cannot be done using the divergence test, because divergence test can be used to show a series diverges. It cannot be used to show a series converges. So let's start with assuming that absolute value of r is less than 1. If you look at the partial sum, so the sum of Rn, n equals 0 to m, this is a geometric sum. So we had a formula for a geometric sum. So it's the first term, which is 1, minus term after the last term, which is r to the power of m plus 1 over 1 minus common ratio. So this is the partial sum of this series. Now if I want to find out whether this converges or not, I will have to take the limit of this. Now if I take the limit as m approaches infinity of the partial sum, r to the power of n equals 0 to m, that is going to be the limit as m goes to infinity of 1 minus r to the m plus 1 over 1 minus r. Now 1 minus r is a constant, so we can take it out. So 1 over 1 minus r can be taken out, times 1 approaches 1 minus limit of r to the power of n plus 1. Since r to the power of n plus 1 approaches 0, I can just replace that by 0. And this is because absolute value of r is less than 1. So that means the infinite sum, the series, sum of r to the n equals 0 to infinity, is going to be 1 over 1 minus r when absolute value of r is less than 1. So if absolute value of r is less than 1, then the series converges to 1 over 1 minus r. Now suppose absolute value of r is more than 1 or equal to 1. Then in that case, absolute value of r to the n is greater than or equal to 1 for all n. And therefore, the sequence Rn does not converge to 0. So by the test for divergence, sum of Rn diverges. So we know the nth term does not approach 0, which means the series must diverge. Okay, so this is a useful example. It's something you would like to, you would need to remember. So sum of Rn, n equals 0 to infinity, is 1 over 1 minus r if absolute value of r is less than 1. Otherwise, it is divergent. Okay, let's move on to another example. As I mentioned, tests for divergence can be used to show a series diverges. It can't really be used to show a series converges. And this example illustrates that. By an example, show that the converse of test for divergence is not true. In other words, so if you go back and look at the test for divergence, it tells us if a series converges, then the terms must approach 0. If the terms approach 0, that does not imply that the series converges. So if you look at the sum 1 over n equals 1 to infinity, this one diverges by an example. This is an example we have done some time ago. This is what we call the harmonic series. And 1 over n approaches 0. So there is a series that the series diverges, but nth term approaches 0. And that is an example that shows the converse. So this shows the converse of test for divergence is not true. Okay, so this is a good example to remember. So that was our first test. In fact, this test that we just talked about, test for divergence, is not a very powerful test. It can't really prove divergence for a lot of different kinds of series that are divergent. And it cannot really be used to prove convergence. So it's not a very powerful test. But it is one of the first things I would try when I'm dealing with the series. Okay, so next is the comparison test. Suppose an greater than or equal to bn greater than or equal to 0 for all n. So I have two sequences, an and bn. Nth term of an is greater than or equal to the nth term of bn. So this means, if I look at the right side, so it means the an is the larger one, and bn is the smallest one. So if you look at the partial sums for an, partial sums of an are greater than or equal to partial sums of bn. Which means if you look at partial sums of an, if this converges, then this would be bounded. But since the terms of sum of Bn are positive or at least non-negative, bounded implies convergent because it is a monotone sequence. So we will prove the first one. If sum of An converges, then so does sum of Bn. So let A be the sum of n equals 0 to infinity. Since an is greater than or equal to 0 for every n, A is greater than or equal to sum of n equals 0 to k for all k. Thus, A is an upper bound for all partial sums of the sum of Bn n equals 0 to infinity. Since if you look at sum of Bn n equals 0 to infinity, this is certainly greater than or equal to 0, and that's less than, up to k, less than the sum of n equals 0 to k, and that's less than or equal to a. So A is an upper bound for these partial sums. On the other hand, partial sums of the infinite series form an increasing sequence. Because if you look at the sum of Bn n equals 0 to k plus 1, this is greater than or equal to the sum of Bn n equals 0 to k, since bk plus 1 is greater than or equal to 0. So it's an increasing sequence. On the other hand, the partial sums of this form an increasing sequence. So it's an increasing sequence. Thus, by monotone convergence theorem, the sum of Bn converges. Because it's an increasing sequence and it is bounded, therefore it converges. Any increasing monotone bounded sequence is convergent. Okay, so that's the first part of this theorem. The second part tells us if the smaller one diverges, then so does the sum of an. So we kind of use a similar strategy that bounded and convergent are the same. So since partial sums of sum of Bn are increasing, or I guess to be a little bit more precise, form an increasing sequence. So they form an increasing sequence that diverges. They must be unbounded above. However, if you look at the partial sums of an, so they are from 0 to k, this is greater than or equal to the partial sums of Bn, n equals 0 to k. And that means partial sums of an this sequence, so the sequence of, let me write it down. the sequence, the sum of n equals 0 to k, where k ranges, k is 0, 1, 2, etc., is unbounded. Because if sum of an were bounded above, then sum of bn would be unbounded above. Therefore, sum of an also diverges. So this proves what we claimed. So it is very important that when you're using the comparison test, you check that the sequences are both non-negative. If the smaller one gives you a sum that is divergent, then the larger one is also going to give you a series that is divergent. If the larger one gives you a series that converges, then the smaller series would also converge. Again, very important to make sure that you check that the terms are positive or at least non-negative. It is okay that if they are negative for a few terms in the beginning, as we discussed last time. The first few terms you can always ignore. Okay, so let's look at another example. Determine if each of the following is convergent. So if you look at 1 over n times 2 to the n, this is certainly less than or equal to 1 over 2 to the n. And I'm going to make sure that I'm checking all of the conditions anytime I'm using a test. As it is the case for any theorem, I will have to check all of the conditions for all n in n. So these are two series, two sequences. 1 over n times 2 to the n is less than or equal to 1 over 2 to the n. Now, the sum of 1 over 2 to the n equals 0 to or 1 to infinity, converges because it is a geometric series with common ratio 1/2. So 1/2 in absolute value is less than 1. So this converges. This is example that we just did earlier. We did this example. I will write it down here. Example 9.1. In fact, yeah, so the first example we did today. Example 9.1. So this converges. So by the comparison test, the larger series converges, therefore the smaller one would also converge. The sum of 1 over n times 2 to the n equals 1 to infinity, converges. Okay, so that was the first example. So the larger, when you drop this one, drop n, you get something larger which converges. Therefore, this smaller one also converges. And as I said again, you have to check these conditions. Make sure you check all of the conditions. So the key conditions are these two, that both sequences are positive and always one is less than the other one. Okay. If you look at the next one, you can compare that with harmonic series, because 1 over n root n is greater than 1 over n for n equals 2, 3, etc. And the reason the denominator of 1 over n minus root n is less than the denominator of 1 over n. And what we know is sum of 1 over n equals 2 to infinity diverges by the second example that we did, example 9.2. Thus, by comparison test, the other one also diverges. The sum n equals 2 to infinity 1 over n minus root n also diverges, which is what we wanted to prove. Okay, so that's good. So we had an example on the geometric sum. We were able to use that for the first one, and then the harmonic series, we were able to use that in the second one. Okay, so far we have talked about comparison tests and divergence tests. Okay. So next test that we're going to talk about is called the integral test. So suppose an is a sequence of non-negative real numbers. Suppose there is a natural number n for which an is the same as a function at n, where f from a capital N infinity to r is a continuous and decreasing function for which f of x is greater than or equal to 0. Then the sum of an converges if and only if the sequence this is bounded. Okay, so let me put that in a diagram. Let's say you have a function like this. So it is important that this function f is decreasing and continuous. So you're gonna have to check these conditions. So the conditions are, I'm going to highlight them: continuous function and decreasing function. Now, the function is basically the same as the sequence. So if you take the values of the sequence at, let's say at 5, it starts being the same. A5 is this value. And then at 6, and then at 7, and then at 8, etc. So if you look at this series, so A6 would be this quantity. A7 would be this quantity. A8 would be this quantity. Because this area is base, which is 1, times height. Height is A6. So this area is A6. The next area is A7. Base is 1, height is A7. The next one is A8, etc. So what I can tell is that the sum of these ANs, n equals 6 to infinity, is less than the integral from 5 to infinity. Less than any of these integrals. I mean, we haven't talked about improper integrals. So less than the integral from 5 to some n. Let's say, so if I go all the way to n, then it would be less than that. So if this is, and both of these are positive, if this is bounded, then this would be convergent, because that would be bounded, which means it would be convergent because the terms are non-negative. So if the integral is bounded, then the series would be convergent. On the other hand, if you look at these sums starting from A5, you get this. You get that the sum of n equals 5 to n minus 1 is greater than, okay, so I'm going to put it on the other side, greater than integral from 5 to n of f. If this is convergent, this would be bounded. Therefore, and this is clearly equal to 0, therefore this would be bounded. So if the series converges, then integrals are going to be bounded. If the integrals are bounded, then the series converges. So that's the idea of the proof. And then we can kind of turn that into a formal proof, not a problem really. Okay, so this is an if and only if statement that we will have to check. So let's start with one direction. So suppose sum of n equals 0 to infinity is equal to sum a, converges. Okay, so let's actually take the series and let's just take, just remove that part because I'm actually going to look at only from n to infinity. So we know that the series from n to infinity, n equals capital N to infinity of an, also converges. So we know this converges. Therefore, the sequence of those partial sums would be bounded. So thus, if I take a look at the partial sums, an would be less than or equal to a. N equals n to k for all k greater than or equal to n. Okay, so now we're going to find the relation here. We know that the series converges, therefore these are bounded. So we're going to write down the inequality. The red inequality is the one I'm going to be looking at. So I know that the function is decreasing. So if I take a look at the integral from n to k, what did they use? They used capital lowercase n. If you look at this, this is the integral from n to n plus 1 plus n plus 1 to n plus 2 plus n minus 1 to n f by additivity. Now, I'm going to replace each one of them by something larger. So the integral from capital N to capital N plus 1 would be less than or equal to the integral a sub n because because f is decreasing, plus integral a sub capital N plus 2 n plus 1 because f is decreasing, all the way to a sub n minus 1 from n minus 1 to n. And this is equal to, this is by monotonicity I'm using. So this is equal to a capital N plus 1 all the way to a sub n minus 1. And this is less than or equal to a because of what we just saw earlier. We know that each one of these is less than or equal to a. So that means integral from n to n of f is less than or equal to a for all n greater than or equal to n. Okay, so therefore it is bounded. Thus the sequence n equals n plus 1, etc. is a bounded sequence. Well, clearly f is greater than or equal to 0. That was given. Therefore, the integral is greater than or equal to 0. So that was given. Okay, so it's a bounded sequence. And that's what we wanted to show. We wanted to show that if this series converges, then the integral would be, sequence of integrals would be bounded. So we're going to do the same thing for the other side. We'll just have to use the blue inequality. So suppose integral from n to n of f is less than or equal to some a for all n greater than or equal to n and a given a, because we know it's a bounded sequence. So we are going to take the sum from sum of a n equals n to k, and we're going to show that this is bounded. So this is, if we look at the, we're going to have to look at the blue areas. This would be an plus 1 plus ak, which is, so I would like to show that this is bounded. So this is less than or equal to an would be less than or equal to the integral of f from n plus n minus 1 to n, I believe. So if you take a look at this integral from n minus 1 to n, so I guess I need to take the one later one. Yeah, if you go back to look at the inequality here, yeah, it started from 6, so one more than the previous one. Yeah, so this would be from n. This would be from n to n plus 1, because an plus 1, this is by monotonicity. An plus 1 is less than or equal to f of x when x is between n and n plus 1, plus integral from n plus 1 to n plus 2 of f, plus integral from k minus 1 to k of f, which is integral from n to k of f. And we know this is less than or equal to a. Thus, the sum of n equals n plus 1 to k, which means the sequence of partial sums of the series n equals n plus 1 to infinity is bounded. Now, since this sequence is increasing by monotone convergence theorem, it converges. And this finishes up the proof. Okay, so last thing we're going to do is we are going to prove the p-test. So what is the p-test and how do we prove that? So given a real number p, the series, this converges if and only if p is greater than 1. So we're going to look at this function. Consider f of x equals 1 over x to the p for x greater than or equal to 1. Now, f is continuous, and so we need it to be continuous and decreasing. But this is if p is positive. If p is positive, it is decreasing. Otherwise, it could be increasing. So if you go back and look at the theorem, it required the function to be decreasing and continuous. Now, we are going to, and then we're going to do an example on that. We are going to now use the integral test. By the integral test, so let's assume that p is positive. We'll take care of the case when p is negative separately. So assume p is positive. So we're going to take the integral from 1 to n of 1 over x to the p dx. Okay, so this is going to be equal to, since x is positive, I can take the integral of this, and what I get is, I get, if p is 1, I get a separate integral. I get natural log of n minus natural log of 1. And if p is not 1, I would get n to the power of negative p plus 1 over negative p plus 1 minus 1 over negative p plus 1. Now, if first of all, the first one, the top one, if you look at the top one, natural log of n is not bounded, because given a real number c, there is a natural number n such that c is more than e to the power of n, and that means n is more than e to the power of c. So that means if I look at natural log of n, this is more than c. So that's not bounded. So thus, integral 1 to n of 1 over x dx is unbounded. Okay, now given this part, we can actually take care of the things that are less than, or p that is less than 1. But let's now first take a look at the second one. We need to know what is 1 minus p. If 1 minus p is negative, in other words, if p is more than 1, then we can find an upper bound for this. So if p is more than 1, then n to the power negative p plus 1 over negative p plus 1 minus 1 over negative p plus 1 is going to be less than. This quantity is negative, so I can drop it. So this would be 1 over p minus 1. And this means integral from 1 to n of 1 over x to the p dx, which is definitely positive, is less than 1 over p minus 1. So by the integral test, it's bounded, the sequence is bounded. By the integral test, the sum of 1 over x to the p converges, or n to the p. N equals 1 to infinity converges if p is more than 1. So far we have shown that, and we have also shown that for p equals 1 it diverges, and diverges if p is equal to 1. So we are left with things that are p that is less than 1. So suppose now p is less than 1. Suppose p is less than 1. Then 1 over n to the p is n to the negative p. Negative p is more than negative 1. So this is more than n to the negative 1 for n, for all n in n. So if we look at this, we can now apply, and clearly n to the negative 1 is positive. Now, since sum of 1 over n equals 1 to infinity, diverges, by comparison test, sum of 1 over n to the p also diverges, n equals 1 to infinity. So to summarize, sum of 1 over n to the p diverges, or let's put it this way, converges if and only if p is greater than 1. And that's exactly what the test was. Now, if you there are other ways of doing that. It would be somewhat easier if you initially notice that, well, sum of 1 over n is the harmonic series. You could eliminate the p less than 1 and equal to 1, and then work on only p greater than 1. It just shortens the solution just maybe a tad bit, but there isn't like a huge difference. Okay, I'm going to actually apply the same strategy for this one now. For what value of p does the series 1 over n to the p natural log of n converges? So first of all, if p is more than 1, then 1 over n to the p natural log of n is going to be greater than 1 over n to the p. I'm going to drop the natural log of n, so maybe replace it by natural log of 2 for all n greater than or equal to 2. And this is clearly positive. Sum of 1 over n to the p natural log of 2 converges by the p-test, because it's just a scalar multiple of the sum of 1 over n to the p, and p is more than 1. Thus, by comparison test, sum of 1 over n to the p natural log of n also converges. Okay, so that's the first step. So for p greater than 1, it converges. Now, if you look at p equals 1, we can apply the integral test. And the reason I think of integral test is that if you look at 1 over n natural log n, that can be integrated by substitution. It is 1 over n, 1 over natural log n times 1 over n, which is the derivative of natural log n. So for p equals 1, let f of x be 1 over x natural log x for x greater than or equal to 2. Now, f is decreasing and continuous over the interval from 2 to infinity, because there is no 0 in the denominator. Natural log x and x are both continuous. So then what I can do is I can just say by the integral test, sum of 1 over n natural log n equals 2 to infinity, converges if and only if the integral from 2 to n of f is bounded. This sequence is bounded. So now we're going to have to take the integral of this. Integral from 2 to n, 1 over x natural log x dx. Now, this one is the derivative of natural log of x. If you look at natural log of x, derivative is natural log of log of x. It would be 1 over natural log x times the derivative of natural log x. And then we have to evaluate that at the endpoints. It is that natural log of 2, which is unbounded. And the reason is, if c is a real number, then there is a natural number n such that n is more than e to the c. So now if you look at natural log of n, that's greater than e to the c, which means natural log of n is greater than c. So I'm going to actually make that c plus natural log of 2. So plus natural log of 2, this becomes plus natural log of 2, which means natural log of n minus natural log of 2 is more than c. So that means the integral from 2 to n of f is more than c. So because of that, the integral is unbounded. The sequence of integrals is unbounded. Thus, the series n natural log of n equals 2 to infinity, this one diverges. So for p greater than 1, it converges. For p equals 1, it diverges. For p less than 1, we can compare it to this one. If p is less than 1, then 1 over n natural log n to the p natural log n is going to be greater than, so since it is in the denominator, I'm going to have to flip the direction of inequality, 1 over n natural log n, and this is clearly positive for n greater than or equal to 2. So now, by comparison test, since the sum of 1 over n natural log n equals 2 to infinity diverges, so does the other one. So does the sum 1 over n to the p natural log n. Okay. And finally, to summarize, we get sum of 1 over n to the p natural log of n equals 2 to infinity converges if and only if p is greater than 1. So this is the conclusion of this discussion. Anytime you're asked to find all values of P that a series is convergent, you will have to find the values of P that are convergent and also show that everything else gives you a divergent series. Okay, so this brings me to the end of this video. We will discuss more tests for convergence of series next time. So I will see you in the next video.